Today I want to be talking about solving inverse trigonometric equations. We will first look at the inverse trig graphs, and they will help us solve the equations later. And then we'll also look at how to apply some trig functions and identities to solve them. So here we have the graph of y equals arc sine x. It is a reflection of y equals sine x in the line y equals x, and the domain is from -1 to 1 inclusive. The range is negative pi over 2 to pi over 2 inclusive. Well, we have to restrict the domain because in y equals sine x, the greatest value of y is 1 and minimum value of y is -1. So now we have that for x. So x must be restricted this way. And for y equals arc cosine x, it works similarly. It is a reflection of y equals cosine x in the line y equals x. The domain is the same from -1 to 1 inclusive because the greatest and smallest value in y equals cosine x is the same as for y equals sine x. So the domain must be the same. The range is different now. It is from 0 to pi inclusive. It's because when we have in the y equals cosine x graph, we have 0, 1, and then we have pi, -1. So we flip the x and y values. So we will have 0 as the smallest y value this time and pi as the greatest y value this time. Now we have the graph for y equals arc tan x, and it is just a reflection of y equals tan x in the line y equals x, and the domain is that x is real numbers. It's because in the graph of y equals tan x, the y values are real numbers. So now it's the same for the domain. And the range is from negative pi over 2 to pi over 2, but non-inclusive. That's because we have two horizontal asymptotes here and there. And here is the graph. I should put a negative sign here. Okay. So notice that this red curve never touches these two horizontal asymptotes. And now let's do some problem solving. Here is an easy example that I found online. Given that x satisfies the equation arc cosine x equals k, where pi over 2 is smaller than k and smaller than pi, state the range of possible values of x. So what you can do here is that you can take cosine of this side and this side at the same time. So by doing cosine outside of arc cosine, you cancel out the entire effect, and then you have one left. Sorry, you have x left. And then you have cosine k on the other side. So let's look at the greatest value. So we know that by substituting this, pi over 2 into cosine, we have 0, and then by substituting pi in there, we can get cosine pi equals -1. So these are the extreme values for x, so x must be between -1 and 0, non-inclusive. Here's a harder example of solving an inverse trig equation. You can pause the video and attempt it yourself right now. I'm going to start explaining. So we need to find an equation to help us solve this weird-looking inverse trig equation. So there is a rule that the sine of an angle is equal to cosine of its complement. So let's say sine A equals cosine B equals x. So that means A plus B equals 90 degrees equals pi over 2. So here we notice that we can write arc sine x and plus arc cosine x, right? Since x and x are the same, and then we're taking this and this, so that means they're representing two angles right now. And if they add up to pi over 2, then that means there are two complementary angles, right? So we just rewrote this rule using like inverse trig, and then we can move arc cosine to the other side, and then we will substitute arc sine x using this into the original equation. And it's kind of messy to have arc cosine in there, right? So like I will let a equals arc cosine x and solve this quadratic equation. You just factor it out and then factor it into the product of these two differences, and then you'll be able to get a1 and a2, and then x1 and x2, and then you can just check them by substituting them into the original equation, and if they match, then yeah, they both work. So that's the answer. X equals 1 over 2 or root 3 over 2. Here are some other examples. So this one asks us to prove that tan arcsine x equals this fraction for the absolute value of x is smaller than 1. So what I did is that I let theta, which is like an angle, equals arcsine x. And what you can notice is that you can move around theta and x, right? So you can move arcsine to the other side. So now you have sine theta equals x over 1, which is x. And what that will remind you of is that you can draw a right triangle, and this angle is theta. So sine theta is x over 1, right? So, and this is x. So you can use the Pythagorean theorem to get the length of this other leg, which is 1 minus x to the power of 2, and take the square root of that. And as for cosine theta, it's just simply this other legs over 1, which is the length of this other leg. And tan theta, which is equal to sin theta over cosine theta, and you just need to divide x using this, and then you'll be able to show that tan theta equals this thing, and which equals tan arcsine x, and that's because theta equals arcsine x, and you just manage to write them all in a long equation, and it's done. So now here is a graphing question. A local artist is creating a mural and blah blah blah, and this artist is shifting this original function, and we want to graph it, and we want to write out the key points, domain, range, and transformations applied on the original function. So to help you graph, I think you can write out the domain and range first, so you know where to end and where to start. So notice that this is the x minus 1. It is a horizontal shift to the right by 1 unit. So now the domain, which is originally -1 to 1 inclusive, it becomes +1 here and +1 here, which is like from 0 to 2 inclusive. And the original range is -pi over 2 to pi over 2, and you add pi over 6 to each side. So now you have this new range. And now you can just graph this whole thing here and mark the important points, such as the y-intercept, the x-intercept, and this middle value, I would say, and then this ending value. And this is also another extreme value, right? So just mark these important points and describe the transformations clearly using the words. Here is another example. It continues on the next page. It is a little long. So we want to find all values of x from 0 to pi over 2 inclusive, such that we satisfy this equation. So the common trick is to take tan on both sides. For tan pi over 4, it is just simply 1. For the other side, it's kind of long and messy. Well, there is a formula that I directly used, which is tan A plus or minus B equals, well, it is in the data booklet, so you don't need to worry about memorizing it, but know when to use it. Yeah, it's kind of messy, but it looks like this. Just apply this and do all the calculations and simplify. Well, because arctan sine x can just be simply turned into sine x, right? And the same for here, we just have cosine cosine x left, and on the bottom we just have 1 minus sine x times cosine x, and that whole thing, this whole fraction equals to 1 here. So we can move this bottom to the other side. Now we have sine x plus cosine x equals to 1 minus sine x times cosine x. There's a little dot here, I'll erase it, okay? And to make it even cleaner, we can move this minus sine x cosine x to the left side. So we have 1 here and everything else on the other side. And here's what I did to actually calculate the result values for x. So let u equal to sine x plus cosine x, because this is really helpful. It helps us to simplify things and factor stuff and to solve. So u to the power of 2 equals sine x plus cosine x to the power of 2. And then we expand it. It will look like this. And notice that sine to the power of 2x, sine x to the power of 2 plus cosine x to the power of 2 equals 1, according to the formula in the data booklet. So it's equal to 1 plus 2 sine x cosine x. And so u to the power of 2 minus 1 and divided by 2 equals 2 sine x cosine x. So we are able to substitute sine x cosine x with something related to u. And this is our clean version of the equation. So now we can simply write u, which is this, plus u squared minus 2 over 2 equals to 1. So now we only have u and some numbers, and we can figure out u easily, and then substitute back sine x plus cosine x to solve for x, right? So now we can multiply both sides by 2, right? So we have 2u plus u squared minus 1 equals 2, and then we just factor and solve, and here are the two possible values for u, which is minus 3 and 1, and now we want to see which ones allow solutions and which one doesn't. So here sine x plus cosine x equals to negative 3. It might look okay at start, but if you think a little more about it, it's actually doesn't make sense. It doesn't, like, there's no x values to make this exist, because, well, let's make a little graph. So this is the origin, and here's the sine curve, and here's the cosine curve, right? So there's a place here, so this is for one full cycle. There's a place on there that allows the greatest value for the sum of sine x and cosine x, and that is right here. Well, that's because for the other values, like here and here, the sum will only be like a middle value, right? So it will only be smaller, and for here it's the smallest, and here is also a middle value. So at here it will allow the maximum sum, and at that point you notice that it's when sine x and cosine x intersect. So we can simply write sine x equals cosine x and move cosine to the other side. We have tan x equals to 1 and x equals to power 4 if we take if we move tan to the other side, right? And now if we substitute power 4 back, you have sine power 4 plus cosine power 4, which both equals to 1 over square root of 2, and in the end it would just be square root of 2, and that is undeniably smaller than 3. So there are no real solutions for this. Let's look at the other side. This is within the appropriate range because it is smaller than square root of 2. So similar to what we did before, we can square this, and this side will still be 1. So this, according to what we did before, this thing can be directly written as 1 plus 2 sine x cosine x equals to 1. And so we can simply write sine 2x equals 0? Well, because there's a formula that this equals to 2 sine x in the table booklet. And since we have a factor here for x, right? So we want to multiply the domain for x, both sides by 2, and now we have this. And we solve for 2x, and 2x can be 0 or pi. So x can be 0 or pi over 2, and if you check them, they're correct. Here is another question that involves some calculus, and that's not the only way to show what the question wants you to show, but calculus is a really clean way to solve this. So you want to show that arctan x plus arctan 1 over x equals to pi over 2 for x greater than 1, and for x smaller than 1, the sum equals the negative value of that. So what I did is that I defined a function. I defined this entire sum as a function that equals to a constant for x not equaling 0. And so I will prove that the first derivative of this function equals to 0 because this function is equals to a constant right here. So the first derivative should be 0. So what you can do is there's in the Descartes booklet there's the first derivative for arctan x, which is the thing, and for that you need to apply the little chain rule. It looks relatively similar. You just need to instead of substituting x in there, you substitute 1 over x in there, and you also need to take the derivative of x to the power of -1 itself, and which is done right here. If you're not familiar with calculus right now, it's okay. You don't have to focus on this question, but here is just a question I feel really important right now for me and my classmates, so I will explain it. And if you keep simplifying this, and then in the end you will have this minus itself, so which is equal to 0, and we prove that. And now we want to try some values for x greater than 0 and x smaller than 0 to show that, oh, f in these values actually equal to pi over 2 or negative pi over 2. So here, I would try x equals 1 for x greater than 0. And if you try arctan 1 plus arctan 1 over 1, it actually equals to pi over 4 plus pi over 4, and that is pi over 2. And for the other, for x smaller than 0, you can try x equal to -1. So arctan -1 plus arctan 1 over -1 is just 2 negative pi over 4 added together, and you will just have negative pi over 2, and you just verified it. And that's how it works. Here's a even more complicated problem. It's not an IB problem, but I found it online, and it's kind of similar to what we might encounter, and it's a very creative one, so I would like to share it. Now, the left side is pretty long, so why not let's move arctan to the other side. So 10 pi over 4 will just give us 1. And we can move x to the other side, so we have 1 over x here. And notice that 1 over x also equals to cosine arc cosine 1 over x, and that will help us write something down below. So this part equals this part, right? We can write it in an even more elegant form, although it's a bit long. That 2 arc sine 1 over x equals to plus or minus arc cosine 1 over x plus 2n pi, where n is an integer. And that is because, well, for example, these two can be equivalent directly, but if you have, for example, negative arc cosine 1 over x here, you will need to add like 2n pi to shift it to match this, right? So here's a more comprehensive way of writing it, and it will help us to find the correct number of solutions. So that's why it's important to write it that way. And now let's not have arc sine and arc cosine at the same time, because that's really hard to solve. So we can write arc cosine in the form of arc sine. So remember, their graphs are not too different, right? We can go back. So for this, you will just need to reflect it against the x-axis and then shift it upwards, and then to obtain arc sine x, right? And to be specific, you will just reflect it against the x-axis and shift it by pi over 2, and then you will get arc sine, right? So now you have several possibilities of equations. So the first is 2 arc sine 1 over x equals to the positive value, like the positive one for this, which is equals to pi over 2 minus arc sine 1 over x plus or minus 2 and pi. This doesn't change because you can shift left or right. And the other side is just the negative one for this entire thing, plus 2 and pi, and you can start solving this and this. So now you add 2 arc sine 1 over x to here. You have 3 arc sine 1 over x equals to this thing left. And for the other side, you will have arc sine 1 over x left on one side and negative pi over 2 plus or minus 2 and pi right here, right? Here, notice that you can get rid of this scale factor 3, right, by dividing both sides by 3, and that's what you have. So for the two possibilities, they will look like this. And since we know that the graph arc sine has a restricted domain, which is negative pi over 2 to pi over 2 inclusive, so that means these values cannot be anything. It cannot be shifted like around forever, right? So for arc sine 1 over x here, for this type of values, we can only have it equal to pi over 6. Well, because if it's like pi over 6 plus 2 over 3 and pi, and for example n equals 1, and then we will have a value that is greater than pi over 2, which is not applicable. The only applicable one is to equal to pi over 6. And so that means 1 over x equals to sine pi over 6, which equals to 1 over 2, and so x1 equals to 2. And similar for the other possibility, the only way value you can have is negative pi over 2, because if you have n equaling like 1, 2, 3, 4, 5 or something, then the values will go beyond the domain and be unavailable, so you can only have this. And so sine negative pi over 2 equals to negative 1, and 1 over x equals to negative 1, then x2 equals to negative 1. And they are correct if you go back and check them. So, and here is another question. That is actually one of the previous test questions we got. If you know how to solve this already, then you don't have to listen to this. And for the other two questions, they're also the test questions we did last time. So if you need a recap for this, you can watch these parts. So with this, same old trick, just take cosine on both sides. And then there's the the data booklet rule for cosine A plus or minus B, which equals to cosine A cosine B minus plus sine A sine B, right? So just apply this rule and help yourself to write this equation into a new form. And cosine 3 pi over 2 will simply give us 0. So now this thing is very long, so we will write it in a more simplified version, and we can move this sine thing to the right side. So this part, we will only have x times x square root of 3 left. So now we have this sine product thing on the other side. We don't want to have sine and arc cosine at the same time. So, and you know that there's a rule, so 1 equals to sine power of 2x cosine. Okay, so that is a rule, so we can apply it. We can write it as 1 minus cosine to the power of cosine x to the power of 2, and then we take the square root of that, we will just have sine x, right? So it's just these two things multiplied together, so we can write it as 2 square roots multiplied together. And we want to use this rule because what it is convenient is that you have cosine and arc cosine, so you can cancel out this like trig effect, right? So you have 1 minus x to the power of 2 here, and under a square root times 1 minus 3 times x to the power of 2 under another square root. Oh, that is because you have this thing to the power of 2, which ends up in 3x to the power of 2. So you can multiply these things together under this big square root right here, and then to solve this, you can square both sides, and then you have 3x to the power of 4 and equaling to this thing. So, and then this will cancel out, so you have 4 on one side and 1 on the other side, so 1 equals to 4x to the power of 2, and then x could be 1 over 2 or negative half. But we want to check whether they actually work by substituting them back into original equation, and you will find that we need to reject x equals to half because it doesn't equal to 3 pi over 2. So, but the other one, x equals to negative half, is true. It equals to this value, so we can only keep the one that is valid. And here is another problem about graphing and writing shorter proofs. So here, you want to describe a sequence of transformations that transforms the graph from the original version of y equals to arctan x to this more complicated shifted graph. So notice that you have 2x plus 1 here, but you need to factor out the 2 here, so you have 2 times x plus half in there, right? So you rewrite it this way, and then now you can describe the transformations properly. So we go by stretching first, so horizontal stretch by a scale factor of half, and then a horizontal translation left by half units, and then a vertical translation up by pi over 4 units. And now this is like an easy part, so we will do B and C, which is just a little bit harder. We want to show that this identity is true. So it will be hard if you want to take tan on both sides because it's just really complicated and might not work. So let's let A equal to arctan P and B equal to arctan Q. So that means we can move tan to the other side. So tan A equals to P and tan B equals to Q, right? And arctan of this fraction, we can rewrite it using tan A and tan B, and it will look like this. It really looks like a formula in the formula booklet, right? Because it looks just like, so this thing itself, it looks like the formula for tan A plus B, the formula for that. So, and we took the arctan of it. So it will just be A plus B, which is here. It will just equal to A plus B. And A plus B is exactly equivalent to arctan P plus arctan Q, and which is allowing us to finish the proof and getting exactly what we want. Now we want to show that arctan 2x plus 1 equals to this sum, for x is a real number greater than 0. So what I did is that I took tan on this more complicated side and try to simplify it to this side. So I didn't write out the full messy fraction. I just go right away with 10 arctan of x over x plus 1. That will just give us x plus 1, which is here. And then 10 pi over 4 is just 1. And same for the bottom, because it's just 10a plus or minus 10b over 1 minus plus 10a 10b, right? So you just apply the rule and then you'll get this. And that's it looks really messy, so we want to simplify it by having these fractions dividing fractions. And notice that the denominators are both x plus 1, so we can get rid of them. And now we have 2x plus 1 over 1. So that equals to 2x plus 1. And if you take 10 of arctan 2x plus 1, you will get 2x plus 1. And since both sides are equal to the same thing, then this equivalence is true. And here is another problem. And it will require us to use the calculator because it's a paper 2. So the scientist is growing 2 plants with different growing speeds. And then first we want to find the initial height of plant B. So HB0, just you don't need a calculator for this question. It's really easy. Just substitute t equals to 0 here, and then you will get 32 centimeters. Don't forget a unit. And for the second question, for part 2, plant A correct to 3 significant figures. It's we do it in a similar way. So it's just HA0 equals to sine 6 plus 27 if you simplify it, and if you plug into a calculator, you get 26.7 centimeters. And now, this question will require us to use the calculator very carefully. Find the values when these 2 plants are at equal height. So that means finding the intercepts using our TI-84. So just write that these 2 functions are equal, and adjust your window, change around your domain and range to see clearly when they intersect. And after you do so, you will find that there are 3 t values where they intersect. Well, at first, because these 3 values are really close to each other and they're really difficult to see, so it might be confusing to know, oh, how many intersections are there? I noticed that this question is worthy of 3 marks, so it's probably that there are 3 valid solutions. And here you just draw a little graph to show how it looks like on the calculator after adjusting the window and stuff. So for t greater than 6, we want to prove that plant A is always taller than plant B. So we need to write an inequality, and so the function for A is greater than that for B, and we can combine like terms, move these things to the right side, and notice that if t is greater than 6, then 5 minus t must be smaller than -1, right? And we know that sine x, like this type of function, will always be in the range of -1 to 1 inclusive. So it will always, no matter what, be greater than or equal to -1. And which is, of course, greater than anything smaller than -1. So this thing always is true. Then sine 2t plus 6 must be greater than 5 minus t. So that means plan A is always taller than plan B after 6 weeks. And that is how you solve this. Thank you for watching.